Welcome back. I wanted to finish up this lecture on 4.1, 4.2 with another quick example and a couple examples. We'll finish out the 12, 13, and 14. So this polynomial, again, it has odd end behavior, you can tell, and so end behavior is definitely a negative up front. So your leading coefficient's got to be negative, and then you're going to be x to an odd power because it's coming out of positive infinity, but it's leaving out of negative infinity. So because of the opposite infinite behavior there, we know it has to be odd degree. All right, and then our local zeros, we've got one. There's a real subtle one right here. I blew this up so you could see that one a little bit better. And then there's another one right there. Man, it's a little tricky. What we have as far as our zeros, we have an even multiplicity zero at -4. We have a linear multiplicity, although you'd have to really zoom in to convince yourself that zero, it's just crossing straight through. There's no flatness at all. And then it bounces off of +1 and for another even multiplicity. All this is a little bit subtle, but I would say our multiplicity for each one of these, so for -4, the multiplicity is clearly 2. The multiplicity at 0 is a little subtle, but I would say a 1 would be descriptive of it. And then we have it's bouncing off of that +1. It could be a 2, it could be a 4. Let's go with a 2 for simplicity. Once we look at the calculator, maybe another idea might pop in our head. And remember, we got to do a leading coefficient. So right now, my guess is that we've got a negative out front. We've got an x plus 4 quantity squared. We've got an x, and we've got an x minus 1 quantity squared. And so that's my rough estimate for what we're looking at for this function, but we're going to check it. We're going to pull out our calculator and we're going to just make sure that this actually works. Now, the scale here is -100 to +100. So here we go. You got a negative x plus 4 quantity squared. You've got an x. That x is representing that 0, multiplicity 1. It's a little subtle in the graph, but it's definitely in there. And we don't need a plus there. We need multiplication. So x minus 1. And we're going to go with the multiplicity 2, although it could be multiplicity 4. It really would help to be able to zoom in even closer. We don't have that option here. So anyway, we're going to hit graph, and we're going to see how it looks. Now remember, we didn't change our y min, y max. Let's go ahead and zoom in on the 0 at the origin. Just I didn't quite hit the origin very well there. So let me go back to a standard window for a second. So I just want to show you that when it crosses through, it's going straight through. There's no flatness. Let me zoom in just a little bit closer to the origin. It goes straight through. It has no flatness at the 0 at 0, and then it bounces off that 1 there in a quadratic fashion. But let's make sure our axes look just like the question, and then we can verify whether we have been successful or not. -100 to +100. Here comes our graph. We could change our y scale to make the tick marks look a little bit better. Let's do that real quick. Looks like they're about 5 maybe on the y scale. So anyway, something like that. And anyway, it looks pretty good. It's bouncing off the axis. It's crossing through the origin, bouncing there. Looks really good. I think we are successful. All right, last couple. Now the graph is given to us, so it's a little bit easier. You can see all these are linear zeros. You can actually tell what the degree is by just kind of covering up these numbers. By covering up the numbers, you get an x times an x times an x times an x. There's 1, 2, 3, 4 powers of x. This is this is, and the leading coefficient, see, everything's positive and there's no negative up front. So this thing behaves like 1 times x times x times x times x, or x to the 4th power. So it is a positive, so as far as end behavior, it's positive x to the even. That's our end behavior. And it determines pretty much what this thing's going to do. So looking for positive end behavior, that one's out, and that one is out. The only choice is A. We don't have to do anything else. But we can double check the other pieces of information. We need a 0 at -2, and we have that. We have a 0 at 4, we have that. A 0 at 5, we have that. And a 0 at 0. So, perfect, we got it all. So, last one. So here's a polynomial with some subtlety about the zeros. That little thing is not actually bouncing off the axis. It's going straight through. So those are actually, that's a linear 0 there, another linear 0 there, a linear 0 there, and another linear 0 there. So be careful with thinking those are bounces. They are not bounces. Let me make it a little bit bigger so we can analyze it a little bit better. And we're almost done. Whoop. Okay, let me make it bigger. All right. So we want to know the factors for this function. Remember, I said this was these are all linear zeros. They go straight through. There's no flatness to them. So this is -1, -2, -3, -4. So at -4 and -3 you have zeros. And then at 1, 2, 3, 4, at +5 and +6 you have zeros. So the factors are, find as many factors as possible. So we have an x plus 4 is a factor. There's an x plus 3 is a factor. It's a kind of weird notation. And you have x minus 5 is a factor, and x minus 6 is a factor. Those are the factors of this polynomial. Now you put them all together into a polynomial, which is just the product of those factors. Product, because the product together makes a 0 for each one of those values. So you have the product of all of those. And you can verify this on your calculator. I mean, once you have figured out what the factors are, it's just going to be x plus 4, x plus 3, x minus 5, and x minus 6. Let's go with a standard window, and we can adjust it to make it look just like their window. So it's not looking great right now as far as the window, but remember their axes are -400 to +400. Ours are not that at all. And then so our x min, x max is -8 to 8, and then they've got this crazy y min of -400 and a positive y max of 400. The x scale looks like it's about 25 apiece. So let's see how it looks. So looking pretty good now. That looks a lot more like it. So I think we've done it. We found our polynomial, and we based it off of those linear zeros, those factors that give you just a single passing through at those 0 points. Is it possible to find any other possible polynomial with the given zeros? The answer is yes, because you could negate it, and that's a new polynomial, and it has the same zeros, but it looks different. And you could actually multiply -2. I mean, you could do lots of things. Same polynomial. Different polynomial, but same zeros. Now, but can you get the same graph? And the answer is no. It is not possible to find any other polynomials with the same graph. Once the graph is the same, the polynomial set. That is what a polynomial is in some senses. It's a collection of all of its points. So if its graph is the same, the collection of all its points are the same. So it's definitely unique. Anyway, thanks for watching. I hope you understand this a little bit better.